a little bit about Muthu. So Muthu is a very known face in RRI. He's been with us for a very long time. I have met him since 1998 as a third-year graduate student, like some of you are now. This is 1998. So he's told us about polymers and polyelectrolytes. I still have his lectures. So, and you'll see that, I can't think of a better way of kicking this off. I'm sure 25 years hence, even all of you, whether you do polymers or not, you will probably definitely retain his notes. Muthu.
Let me thank Ranjini for her kind words. Don't go away yet. I know how hard it is to organize something like this. And you and Mahesh were interested in doing this for almost 4 or 5 years, right? I remember my first email, which we had correspondence with. Thank you so much. Okay, so I do not know how life began on our planet, maybe 4 billion years ago. Maybe our landscape was looking like this. Maybe it launched some chemical reactions. I really do not know how life started. But I do know the language of Mother Nature. That language is polymers. And why do I say that? Let's look at the temperature, right? In degrees Kelvin, that's the temperature of the surface of the sun. And that's 0 degrees Kelvin, that's the lowest. And we are living in this very, very narrow range, right? The temperature of the human body is around 310 degrees Kelvin in this scale, only very narrow. And if we make an error of 1 degree Kelvin in our body, I would not be here, right? Our delicacy of our human life depends on very, very narrow range of temperature. That's where I'm speaking, you are listening, and we argue, discuss. All these things are happening at a very narrow temperature range. How is that possible? It's possible because we do know, right? Fundamental physics, the free energy is energy minus temperature times entropy. And temperature is fixed, essentially fixed. But if we dance and sing, molecules open up, compactify, do lots of things, they communicate. All these things are happening because the candidate that the Mother Nature chose must have the capability of exploring or expanding and exhibiting a tremendous variations in conformational entropy. Otherwise, life would not happen. What is the best candidate to have that capability? Even in terms of this little wire, if I have, right, this is a polymer, I can stretch it out, right? I can stretch it out, it's very long. I have a contour length long. But that's not the way the polymer exists. They actually coil up because they can have lots of entropy, conformation entropy. Not only that, it's not only one conformation it can assume, it can assume different possible conformation, infinite number of conformations can assume. Therefore, entropy is very large. And then I can malleate, I can deform, I can do a lot of different things with these conformations. And as a consequence of this, the entropy can be manipulated, can be used as an engine to express life. And that's the reason why I believe that Mother Nature's choice to express life is polymers. No wonder today we are talking about soft and living matter. Good choice. Good choice. It's soft because of all these things, right? No, I'm going to move around. It's very soft. And I'm going to exhibit entropy. And if you pay attention to even children, intuitively, when they don't draw a compact sphere. They don't draw a straight line. They draw something like this. Right? If you watch any of the children around, so natural for them. So does Mother Nature. That's how she, the nature express life. So not only we can talk about life processes, but also we can make materials. And that's the title of our workshop this week or these 3 weeks. Okay, so given that, if I go to a mammalian cell, right, it is a Coulomb soup. That means what? There are lots of charges. There are electrostatics. And that is physics, fundamental physics, charges, right? How do they interact? So when we talk about all these organelles in a mammalian cell, the way molecules move around, I can put my pointer anywhere on this screen. I will see a macromolecule, DNA, RNA, proteins, polysaccharides. And they are in a salty water, crowded salty water. So I call this to be Coulomb soup. So the theme of my presentations would be this and two more, is in terms of how macromolecules play a significant role in soft and living matter. So that's basically my approach to what I want to share with you. Okay, there's a preponderance of macromolecules. What are they? For example, if I take, for example, polysaccharide, polynucleic acid, double-stranded DNA, RNA, or a polypeptide proteins, or even a synthetic polymer, you see the charges here, right? This is a phosphate group. There is another group, carboxylic acid group. Here is another negatively charged group, positively charged group, negatively charged group. There are lots of phosphates here, lots of phosphates here. So we have a lot of these molecules in nature, and they carry charges, negative charges, positive charges. But when you point out DNA, for example, or RNA, that molecule does not exist alone, right? If you take a polymer like this, and I put lots of charges on them, this is almost like it will explode. The repulsion between these charges would just explode. That's not stable in this universe. So they cannot exist alone. The way they would exist is to have partners. The partners are called counterions. They are oppositely charged ions. If I go in here, this is a phosphate group, that's sodium. When you want to order DNA from some catalog, some vendor, they will give you sodium salt or potassium salt. They'll give you salt, not as a molecule itself, because that's not stable. So these molecules are not alone. They are accompanied by counterions, water and salt. And correspondingly, we have lots of forces and structural organizations which are helping them to move around and exhibit their properties. That's how it's really a collective behavior. So in this Coulomb soup, let me point out the basic ingredients. The basic ingredients are this. If I take the contour of a polymer chain, here, for example, a polynucleotide, there's base, there's sugar, these are phosphate groups, negatively charged, there are counter ions, there's a counter ion there, and salt ions in this salty water. And there are van der Waals, which we call extra volume interactions between one part of the chain with another part of the chain, hydrogen bonding, structure of water always changing. So what we see in this Coulomb soup is a confluence of topological correlations. When I say topological correlations, that this monomer, this repeat unit knows that it is connected to another repeat unit through the chain connectivity. So there is a topological correlation due to chain connectivity, of course, the electrostatics, and there's a flow, there's hydrodynamics. And all these three aspects are long range. Chain connectivity, one monomer knows about another monomer of the same chain or another chain. And of course, electrostatics is long range. And of course, hydrodynamics is also long range. So the confluence of these three major long range attributes results in a very huge collective behavior. And then as a consequence of this, what we know is every molecule is able to connect with every other molecule at the same time, and they work together. And that's how we have the manifestation of this soft and living matter. That's how it comes about, right? And as a result of this, we have a wonderful life coming out of this collective behavior. So this is the introduction to what I wanted to say about the premise of our research, our goal. So let me talk about this topological correlation. So as an introduction, what I will say is, as I already pointed out, the chain is not going to be stretched out. The chain is going to be like this. So there is a length of this chain. Let me write that to be n. If I stretch it out, how many monomers are put together? And then there is also three-dimensional size or shape. It looks like a coil. Let me call this to be radius of gyration. Some ball of wool, there is a typical radius. So this radius of gyration is proportional to, it turns out, to be some number which we'll call exponent, some exponent. If it is stretched out, nu would be 1. If it's like a compact sphere, that'll be 1/3, because n is proportional to mass, right? So therefore, Rg cubed would be a mass that's more like a ball of steel. So nu would be 1/3, right? But that's not common behavior. The common behavior is something between 1 and 1/3. What's the consequence of this? The consequence of this is the following. Suppose I take this and then look at some distance r from the center of mass, and then I count the number of monomers and look at the density, monomer density. If I plot monomer density as a function of r, what you'll see is, which we'll talk about it in about 10 minutes or so, it's going to decay like this. And in fact, this decay is more like 1 divided by r power 3 minus 1 over nu. That is this nu, this exponent. In the literature, this 1 over nu is called a fractal dimension because it is a self-similar object. Let's not get into mathematical technicalities, but typically it goes like this. Suppose nu is equal to half, as an example, somewhere in the middle, then this goes like 1 over r. 1 over r is a long range. So already the density is decaying like 1 over r. That means they are correlated, long range correlated. So this is long range. Long range topological correlation. Okay, that's about chain connectivity. That's what I'm saying here. Radius gyration is proportional to molecular weight, chain length, power nu, that's size exponent, chain connectivity, and the long range topological correlation. That's aspect number 1. And usually it is somewhere in this range. Now let me go to the charges. How do we think about the charges? For the charges, suppose I take, say, some charge in here, so Z I E. Z I is 1, 2, 3, something like that. Typically 1 or 2, usually 1, plus 1 or minus 1. And then I have another charge here, Z J E. Let's say the distance between them is Rij. What is the interaction between them? U Ij, let me write in terms of thermal energy, Boltzmann constant times temperature. You know from electrostatics, this would be Zi, Zj, E square divided by 4 pi. Epsilon naught is permittivity of vacuum. This is epsilon is a dielectric constant of the medium, whatever medium the charges are embedded in. And then I have 1 over Rij. And clearly this is also, and kBt. Clearly this is also long range because 1 over R. So if I plot this Uij by kT versus R, this is 1 over R. Electrostatics, long range. Now, this is dimensionless. This is 1 or 2 plus or minus. This is number, 1 over distance, length. Therefore, this better be length. This has to be a length. This must have the dimensional length. Let me call this length to be Beerem length. And I'm going to give a symbol LB. This will appear again and again. So what's the meaning of this Beerem length? If I bring these two charges at a distance, Rij is comparable to this number, Beerem length, for monovalent charges is plus 1, 1, plus or minus, doesn't matter. The strength of the interaction, the electricity energy is comparable to kT, because then that becomes 1. Monovalent. This is 1 when this distance is equal to this. So if I plot Rij, the distance between two charges, as a function of, say, dielectric constant, because the Beerem length is 1 over epsilon. So if I plot how this Beerem length is going to look like as a function of epsilon is going to look like this. 1 over epsilon, theorem length is 1 over epsilon, it's going to look like this. So if the distance between the charges is less than the theorem length, if this is less than this, right, it will be strong interaction. Right? If this distance is less than this number, this is a large number, so I have a strong interaction. Electrostatics. On the other hand, if the distance between the charges is larger than the theorem length, then I have weak interaction, weak electrostatic interaction. Weak interaction. So this sets, this length sets the scale of energy. All right. Whether we talk about strong electrostatic interaction or weak electrostatic interaction between charges, everything depends on theorem length. That means it depends on the dielectric constant. That means it depends on the polarizability of your Coulomb soup. Right. So if you right, that's the one that sets the energy scale. How molecules are going to be clinging together, ions are going to be clinging together or going to move away. Okay, so this is the energy scale, and we write it in terms of length, right? Because that's the distance at which I'm going to see whether it's going to be strong interaction or weak interaction. And remarkably, for water at physiological conditions, room temperature, this LB is about 0.7 nanometers. 0.7 nanometers, right? Very delicate. Now, it's not of very large length scale, it's not atomic length scale. That's a number that comes out in terms of. So let me summarize this again. Again, I'm just repeating myself. Two charges, isolated pair of charges, electric interaction like that is a long range. Theorem length is defined that way. That's about 0.7 nanometers. So whether I have charge interaction being strong or weak is given by that simple box formula. Okay, this is a very important concept because when we build our picture in terms of assembly of large molecules, macromolecules to have certain functional properties, these are the common things, the fundamental things that they come into play in designing your theoretical framework as well as the experimental expedition. Now let me go to another situation. This is when the two ions are alone. But I already told you that it's a crowded environment. There are lots of ions in the solution. Right? It's a salty. Typically, we talk about 0.15 molar, 150 millimolar, typically in our human body. Right? So that means we are going to have lots of ions in here. Some plus ion there, minus ion here, has to be electrically neutral, plus things like that. When we have the other ions in the solution, the interaction between this charge and that charge is not given by this. Instead, it's given by the theorem length I wrote Rij, except now it is a minus Rij, some number kappa Rij. That's what will happen. It is not going to be like that one. Instead, it's going to be screened because it's exponentially screened. Now, what we'll have is we'll have something like this. That kappa is called inverse Debye length. We write this to be 1 over CD. CD is Debye length. So this kappa is, right, 1 over CD. It is minus Rij divided by CD. That is, let me write the Debye length in here. So for distances shorter than Debye length, there is the electrostatic interaction felt. For distances larger than Debye length, the electrostatic interaction is weak. So this gives me a range of interaction. Theorem length gave me the strength of the interaction. Now Debye length gives me the range of the interaction. And remarkably, this Debye length is again 0.7 nanometers for water for salt concentration, CS salt concentration is about 1.15 molar, 150 millimolar. That's our physiological salt concentration. So the Beerham length, which gives me the energy scale, and the Debye length that gives me the range, they're comparable. And that's how the delicacy of our living process comes about. So let me show that in here. So I have, when other ions are present, it gets screened, electrostatic interaction gets screened. And for monovalent salts, like sodium chloride, potassium chloride, we have the Debye length going like 1/2 square root of CS, and that's about 0.7 nanometers. Instead of this long range interaction, now it becomes, it's still long range, but it's screened out. And this is my Debye length in this scheme of things. This is the electrical potential. There is one more complication. The complication is this. Okay, these are two important concepts, right? But the complication is this. If I take my polymer, right? If I take any polymer, DNA or RNA, synthetic polyelectrolytes, what happens is this. Almost all charged polymers, the backbone is oil-like. Without charges, they would not mix with water. We do know the dielectric constant of oil is like 2. Right, coconut oil, dielectric constant is 2. Water is 80. So the interface between the polymer and the water, they are coming from the charges. Minus, minus, minus. They are coming from the charges. So here I have dielectric constant 80, but in here it's a 2. That means there is a gradient in polarizability. It's a cloud. There is a region near the backbone of the chain where the dielectric constant is low. I already told you that if the dielectric constant is low, right, for any Rij, the ions are going to bind. If they are oppositely charged, they are going to bind because of strong interaction. If the dielectric constant is large, they are going to be weakly bound. So although I have DNA, uniformly charged DNA, put in water, salt, DNA salt, but when I go very close to the backbone, the ions, the counter ions, would prefer to bind with the backbone. When it's away from the backbone, they will enjoy their translational entropy. So there is always a trade-off between translation entropy of these ions and a binding near the backbone of the chain of the opposite charges. So therefore, although I have uniformly charged DNA, it is never uniformly charged because of the counter ions binding with the backbone. So you have a mixture of charged groups and the ion pairs. When a counter ion binds, what does it do? It makes a dipole, right? Maybe a temporary dipole, long-lived dipole, but it makes a dipole. So you have a mixture of monopole interactions as well as the dipolar interactions, right? Instigated by dielectric mismatch, polarizability differences in the proximity of the polymer and away from the polymer backbone. And that leads to very beautiful phenomena, in fact, and that's the one that controls many assembly processes. And here is charge regularization. How does that happen? It's not, right? This is the backbone environment. The polarizability is different from the polarizability away from here. This ion is a translationally free. It enjoys its entropy. But in here, when it binds, right, this counter ion binds in here, it'll make a dipole. There's going to be a dipole here. So because of this dipole formation, we'll have dipole-dipole interactions. And that's the basis of the Keystone forces, dispersion forces, van der Waals forces, everything. That's the basis, dipole-dipole interactions, 1/4, 1/6. Now, in the case of polymers, these Keystone forces get amplified because there are many dipoles in a small region. Right? Therefore, there's a natural tendency for these molecules. They are also charged, completely uniform. Chemically, they are supposed to be charged, but they are not. Because of this dielectric mismatch, we will have a tremendous amount of attractive forces, which we'll talk about probably tomorrow. Plays a major role in the assembly of these large macromolecules. And there are formulas given here, one can work it out. But the important thing to note is that there's a negative sign, dipole-dipole interaction. Okay, so now I'm going to stop for a second. And I want to tell you about polymers. How do we think about polymers? So I told you about this one, right? There's a nu here. And I told you about the charges. But now I want to build the picture more properly so that we can use it as a tool to tinker around making new materials or understanding life processes. How do we do this? Now, this is a place where I need to spend a little bit of time to explain the basic things about how we go about. We have to respect chemistry, right? When you make a polymer, so here is one carbon atom, another carbon atom, I have like this. And as you know, the sp3 hybridization, tetrahedral bond formation, one group goes there, another group goes there, let's say that's hydrogen, hydrogen, and I have bond, another one like this, like that, and on and on. Right? But if this cannot persist, as I already told you with my wire, it likes to bend at usual temperatures that are of interest to us. It will bend instead of going like a zigzag, zigzag, it will bend like this. You go down like this, like that, like that. Then again, it'll bend like this, like that, and on and on. If this is a situation, would it be worth my time to go and pay lots of attention to the chemical details in here? It is important to respect the chemical details, but at the same time, I want to have a big picture of how these molecules are going to behave at a large length scales. Because when you take a mammalian cell, we are talking about microns, 50 microns, right? 100 micron length scale. I don't want to take the burden to address what happens at, say, 0.1 nanometer or 0.2 nanometers. So I want to somehow devise a mechanism of parameterizing the chemical details. That's what I want to do. So why don't I do the following, right? Let me imagine, this is my imagination. Let's imagine it's not me, it was done by Kuhn. Let's imagine that the orientation of this bond persists only for a short distance along the backbone of the chain, and then it's going to bend. So let me call this to be one segment. Let me call this to be another segment, on and on. That means the orientation of this segment, direction of this segment, is uncorrelated with the orientation of this segment, and on and on. So this means if I do this, this picture now is equivalent to something like this. This is Rayleigh's random flight situation, right? I make a step. After making a certain step, I figure out in what direction I went. I take a random direction. I make another step. After a certain time, then take another step, on and on. So what I do is I imagine the trajectory of a random walker is equivalent to a configuration or a conformation of a chain. This is just an imagination. And we all know about random walks. If that's the case, I can make a basic guess. Let me say there are n steps, and this would be called n Kuhn steps. Let me call the length of each step to be L, n steps, each of length L. Let's do that. Then the mean square displacement, the distance that I travel square, end-to-end distance, this is like a diffusion law. Mean square end-to-end distance would be equal to n L square. And for random walk, I can also calculate radius gyration. Radius gyration square would be equal to n L square divided by 6. Sorry, n square over 6. That means radius of gyration goes like n power half, according to this simple argument. So that's my nu, right? The nu that I told you before is that number. If I do not have any consideration of interactions between segments, if I have this and I don't worry about banging, I don't do anything like this interaction, I don't do that. I'm not allowing that. This hypothetical case, if you only worry about connectivity of the chain, just conformation entropy without any interactions, then for a flexible chain, the answer turns out to be simply right away, turns out to be half nu is equal to half. Right? This nu is equal to half. That means 1 over R. So entropy correlation, chain connectivity correlation alone, without any interaction with either solvent or between the different segments, I have very profound results, namely 1 over R. Okay. Now let's look at the consequence of this. Since it's a random walk problem, we know the probability distribution function. Suppose I want to know, I start with one point in here, at the other end is R. So I have my polymer chain like this. That distance is say R. What is the probability of finding R after making n such steps without any other interactions? The subscript means there are no interactions, no extra volumeter van der Waals interaction. This you probably know already can be written to be 3 over 2 pi n L square. That's the probability distribution function. Since for large number of n, this is the probability distribution function, we call this chain to be a Gaussian chain, because this distribution function is Gaussian. This is a Gaussian chain. That's a nomenclature. And the properties of this are very well established. We can do with the paper and pencil. Now let me go and show. Is this my computer? Yes. Yeah, sure, please. Thank you. You hit B. You hit B to show up. There we are. Okay, could you please scroll it down a little bit? I'm just repeating here. This is the Kuhn model, random walk chain, which I have written there. Please scroll up. You could? Do you want me to do it? There. All right. So that's my probability distribution function here. It's a Gaussian chain. So I showed you on the board very quickly. But if you want to account for interactions, we want to have very fancy, sophisticated mathematical tools. It is advantageous to write this simple distribution function like a diffusion equation, partial differential equation, or as a path integral, Feynman path integral, free particle path integral. And if you have interactions between two monomers with some VR that appears in there, then that gives us a technology to go and compute entropy, energy, free energy, not only for one single molecule, but for a collection of molecules. And in fact, this is equivalent to time-dependent Schrodinger equation. We can formulate this. So all the quantum field theory that we know, Feynman diagrams, all those things we do, we unleash the technology to actually go and figure out, compute, and then compare with experiments and go back. Next one. Okay, so I could probably show right away. So if I go and look at the free energy, forget about that constant, free energy of single chain, based upon this result, this is probability, right? Entropy is equal to Boltzmann constant times the logarithm of P. So that will give me, apart from constants, logarithm of P. This is a constant that does not, entropy to have certain end-to-end distance R. This is a constant that's not going to do anything to me. So the important thing is this term. So that's going to give me minus 3 R square over 2 and L square. And free energy to have a distance R E R minus temperature entropy at R. There's no energy here. I told you there's a phantom chain in this model. Gaussian chain, there is no entropy energy there. So I put minus T times that. That gives me 3 R square over 2 NL square. That's my free energy. So if I plot free energy as a function of R, it's going to go like this. I already told you the minimum free energy must be consistent with this result. So there is a value here that would be square root of n times L. That's the minimum here. R larger than that equilibrium value is like a Hookean spring, parabolic dependence on R. That means the force constant, right? That's like, therefore, let's work it out. So the force constant would be this number. So F of R, and there is a KT, D by 2, there's a KB in here, and also there's a T here. So the force, free energy, goes like temperature divided by N R squared, apart from prefactors. This is magic. This is absolute magic. Because what it means is, looks like it's a Hookean spring, and the spring constant is proportional to temperature, which is kind of fixed. But the amazing thing is, it is modulated by N, length of the chain. If I make the length of the polymer longer and longer, it becomes softer and softer, because the force constant is 1 over N. If N is at 10,000, imagine it's very soft. 10 to the minus 4, 10 to the minus 5 force constant. You can modulate it. And if you change the molecular weight, protein is a shorter one, so DNA is, or RNA or DNA are very large. So you can play this malleability of this soft matter, but just playing with the molecular weight, that insight comes even with the paper and pencil argument. Very simple argument. That's what happens to me. Okay, now let's go back to, thank you, Gopi. It's able assistant, thank you. All right, so, and at the same time, I want to make sure, so you want to do it in a more careful way. So this is the parabolic behavior for expansion. When you compress it, it also resists, because you cannot compress it more, and one can work out properly. And then when you do this, this is a free energy diagram. And then the tensile force, I already told you. But in general, you cannot stretch the chain forever. If it's a phantom chain, you can stretch it. Gaussian thing, you can stretch it forever, but that's not true. When you account for the finite extensibility, then the force versus the distance, end-to-end distance in that unit will go like this. So it has to break. You cannot stretch more than its a contour length. And when you do that, this Kuhn model with a finite extensibility is called a freely jointed chain model. You'll see this in the literature again and again. That's the meaning of freely jointed chain. Right? Finitely extensible freely jointed chain. Next one, please. Okay, so when I talk about this molecule, so far I have been talking about completely flexible chains. And I already told you here, there is some distance below which the orientation of the bonds are correlated. Beyond certain distance, they are not going to be correlated. When I lower the temperature, the rotation around these bonds will become harder and harder, because there are always the barriers, right, due to chemistry of the constituting in the various molecules. Therefore, when I lower the temperature, the barrier will become large, effective barrier will become large, it becomes stiffer. So therefore, this persistent length, where the bond orientation is going to be persisting, will become longer. So the way you deal with that is to go through a very simple Kuhn model. But now what we do is we account for the fact that there is a bending energy, and which is depends upon temperature. Therefore, there is a persistent length. If you look at the segment orientation correlation function, you can exactly show paper and pencil calculation. You can show it's exponentially decaying as a function of the distance between the repeat units. And the correlation length there is a persistence length. And if the persistence length is short, of course, you will get this is Kuhn chain result. R square will become L. L is contour length times L. And on the other hand, if the piercing length is very large, then it will be rod-like. So at the low temperature, particularly for synthetic material, low temperature, right, then the chain will become rod-like. Unless if it's a double-stranded DNA, short double-stranded DNA, it will be rod-like because the contour length is short compared to its intrinsic persistence length. On the other hand, if I have a very large double-stranded DNA, locally it's rigid, but the contour length of double-stranded DNA, like I say, 27 kilo base pair, for example, that is so large compared to the persistence length, then it will look like a Gaussian chain if you don't account for the extra volume interactions. So you have a crossover. This is called Kratky-Porrard model that I have written on worm-like chain model. So you go between one limit, Gaussian chain limit, to a rod-like limit in a continuous way. At low temperature, the chain will become stiff. Okay, thank you. Right, now we can stop for a second, please. Now what I want to do is I want to go and talk about the interaction, extra volume interaction. Okay, thank you. So now I have been ignoring, so far I have been ignoring interaction between segments. So now what I'm going to do is I'm going to look at interaction between segments. So what's the consequence of that is? So in order to do that, okay, I can't find white chalk. Thank you. All right, so I have one part of the segment like this, and I have an interaction between this and this. Now, when I put this polymer, it's not in vacuum. Polymers do not exist in vacuum. I have solvent molecules here. So what I need to account for is the interaction between this monomer with that monomer or that monomer, interaction between this monomer and this solvent molecule, and also interaction between this solvent molecule and that solvent molecule. So I have to worry about all these things. This is an incredibly difficult problem. Even with the modern computers, we cannot do this properly, let alone calculating polarizability of such media. So if I write the interaction energy, U, between two, say, I and J monomers, Uij, if I suppose I plot as a function of the distance between them, if they are far apart, there is no interaction energy. That's going to be 0. If they are too close, it's going to go to sky high because the repulsion, the electrons cannot overlap. So it's going to be there at short distances. And as you can intuitively expect, but you can theorize and can show, because of dispersion forces, van der Waals interactions, the shape of this would be like this. So where this minimum occurs and what is the magnitude of this attractive energy depends upon chemistry. And there are infinite number of polymers in the universe, right? So in order to calculate this for each one of them is a daunting task. What we like to do is we like to parameterize the chemistry in terms of physically measurable quantities. In order to do this, we calculate second wave coefficient between two segments inside a polymer chain. Let me write that as a parameter. That's V is a parameter. That will be, let me write L cubed in terms of segment length, D cubed Rij, 1 minus e to the minus Uij by Kt. The second wave coefficient. Let's just stare at that formula and look at what the consequence is. If the temperature is high, I'm going to feel interactions here, repulsive interaction, just like gases, right? But they are banging against each other. So when the temperature is high, this is highly positive. If that's positive, temperature is positive quantity, that's positive. E to the minus a large positive quantity will go to 0. So this plus 1 term is going to dominate. So if I were to plot this parameter V as a function of the temperature, at high temperature, it's going to be positive quantity, because this is going to be not important. On the other hand, if the temperature is low, I'm going to feel the attractive interaction. that means it's going to be negative. If it's a negative, low temperature, so large number, this is negative times negative positive. E to the large positive number is going to be very dominant compared to 1. So this is going to dominate, but I pick a negative sign. So this V will become negative here at low temperature. So naturally, I should see something like this. Yeah, you can put on a computer, calculate it, do the integrals, you can do this. That's what happens. So there is a special temperature at which V turns out to be, appears to be 0. If the extra volume interaction is a 0, that means more like a phantom chain, the Gaussian chain that I talked about. So this temperature is called a special theta temperature or Flory temperature or ideal temperature, where the Gaussian chain statistics appears to be operated only at the delicate temperature. If the temperature is lower, then attraction is important. If the temperature is higher than theta temperature, repulsion is important. This is positive, this is negative. So how do you account for what's the consequence of this? Let me do a very simple calculation to show how we do this. So I already told you here, due to entropy alone, the free energy chain connectivity alone without any interactions, f of r goes like r squared by n. Forget about all the other unimportant quantities. This is due to conformational entropy, topological correlation. Now I have this extra volume interaction. Let me talk about high temperature phase. So per contact, 2 monomers coming in here, it's V, is the strength of the interaction is positive. And what is the probability I'm going to find 2 monomers very close by? That's going to be n by 3 dimensions, r cubed. R is radius, r cubed is volume, 4 by 3, forget about it. N over r cubed squared. Probability to find 2 monomers in the same location is going to be density square. And this is the strength of the pairwise interaction. Now I'm going to talk about the whole coil. The volume of that coil is r cubed. Therefore, what I have is r squared divided by n plus v, forgetting my prefactors, n squared divided by r cubed. This is my free energy. What would be the optimum value of this free energy? Right? That is optimum value of the r. That will be df by dr. That's equal to, right, r over n minus, forget about 3, v n squared over r to the 4. That's equal to 0. That gives me r going like v to the 1/5, n to the 3/5. That's very quick and dirty calculation we can make. So suppose I make a measurement of radius gyration. This implies radius gyration square of this, divided by molecular weight, degree of polymerization. So they'll give me v to the 2/5, n to the 6/5 divided by 1 factor of n is out. So n to the 1/5. This means experimentally, I measure radius gyration square. I know molecular weight and I plot this as a function of n to the 1/5. I should get a straight line. If any of these things makes any sense. And the slope of this is v to the 1/5. That v depends on the chemistry, right? It's a parameter. That v depends upon, I think I always over there. That depends on the chemical details of how the different solvent molecules and particular chemical details are contributing to this value of v. Okay, that's the prediction. That's one. Good. All right, let's go to the next one, please. Next one. Of course, absolutely.
So I just wanted to tell you that please feel free to raise your hands and interrupt.
Absolutely.
Okay, because this is a school style lecture. Don't, try not to miss anything. It's all up on YouTube, but please interrupt. Yeah.
I was informed that it's going to be a question and answer session toward the end.
Also.
But you are always welcome to interrupt. Always. I hope it's clear enough. Okay. All right. Okay. So this is my radius. Based upon this calculation, I get this prediction: v to the 1/5, n to the 3/5, and I have plotted it for an experimentalist point of view. Next one, please. Okay, next one, please. Okay, so now let's go to low temperature. Okay. Let's repeat the same calculation that I did over there. The way we do that is now, suppose I have this V to be negative, right? Suppose V is negative, then the free energy, minimum of free energy would be V is negative. That would be R being 0. That's negative. If I want free energy to be minimum, R being 0, that is crazy, right? That's like more like a black hole. That's not possible because these are physical objects. So when you compress it, the 3-body interactions will come in. Not only 2-body interactions you have to work out, you have to do 3-body interactions. So let's put a 3-body interactions. So this is the energetics associated with 3 monomers interacting. And then the probability to find 3 monomers would be N over R cubed power 3, right? And then volume, multiply volume. So you get N cubed by R to the 6. So you put this in, you calculate this, again, exactly where we did there. Then the prediction is at low temperature, when V is negative at low temperature, our radius goes like N to the 1/3. Now, there's no entropy because they're all collapsing, makes a globule, compact sphere. So that's the prediction based upon this kind of argument. So let me summarize this. The summary is this. If I take radius gyration at high temperature, nu is equal to 3/5. And we call this to be a coil, swollen coil. If the temperature is below theta temperature, much below, then the exponent that I introduced right in the beginning, that nu, is 1/3. And there's a special condition for a particular pair of polymer and solvent, which is the theta temperature or Flory temperature, at which nu is equal to half. So this is the typical graph that we would expect for a single polymer chain, no charges yet. On the other hand, there is another branch. If I lower the temperature, because of the chemistry, the locally it can become stiff, then I can go to a rod-like situation, then nu is equal to 1. Right? So this is the general premise of how a polymer chain can behave in solution alone, without any charges. Okay, that's a quick summary. Next one, please. Is it really correct? You know, I can work on the blackboard from left to right as much as I want, but I need to talk to my experimental colleagues, or I do my own experiments, figure out whether this makes any sense. Let's check. Here is an example of different kinds of polymers, different solvents. And I told you there's a prediction there. Rg goes like V to the 1/5 or N to the 3/5. I even showed you Rg squared by N should be a straight line with the N to the 1/5 power. And then that slope is that number V power 2/5. And that V is related to all the chemistry. So look at this straight line. Beautiful data, right? Rg squared by N versus N to the 1/5. These are all perfect statements for entirely different systems. So there is a universality in terms of this big picture of how they depend on molecular weight, degree of polymerization, that exponent. But the chemistry comes in terms of the slope. The slopes are different. That's because B power 2/5 is different. Now let's go to unfolded proteins. Look at the data point. There are so many unfolded proteins for different lengths of the proteins. And that slope is 0.6, 3/5. Radius gyration versus this one, double logarithm plot. So it doesn't matter whether they're synthetic systems or natural systems. So that simple calculation that I showed you is valid. This is the way we build our picture in terms of addressing these complicated systems. Now let me go to the other extreme. This is a synthetic system, right? Radius gyration as a function of temperature. This is coil-like. This is globule-like. And Rg, when you analyze the data for different molecular weights, this law is borne out. And here is a folded proteins. If you look at the radius gyration versus length of the folded protein, then you get a slope of 1/3. So we are on firm ground in terms of the simple way of thinking is actually effective. It's okay to think simple. And in fact, it's advantageous to think like this, so surrendering to a very complicated way of addressing the problems. Okay, so what happens if these molecules carry charges? Okay, so I gave the outline. So what happens? That's our primary goal. How much time I have? 15 more minutes? How do you go about this? I already told you about this a little bit. So let me go back and tell you a little bit about charges again. Right? And then we had to combine this knowledge on this side and this knowledge on the left-hand side there. That's on charges. These are all our uncharged polymers. And that's what we are going to do in the next lecture. But now let me remind ourselves again about that problem. Okay. Next slide, please. You know, recall basic electrostatics. In vacuum, Gauss law, del dot E is the charge density. And epsilon naught is permittivity of vacuum. The electric field is a negative gradient of the potential. And substitute this there, you get Poisson equation of del square C is equal to minus rho by epsilon naught. The generalization of that in the ponderable media, dielectric media, polarizable media, water, etc., is the following. Gauss law, instead of E, we have electric displacement, which is proportional to E. And this is a dielectric constant tensor. It's not a constant, dielectric tensor. It can be anisotropy. It can depend on electric field. Substitute this, all right, this expression into the Poisson equation. Substitute this there. Then we have divergence of this one dot grad psi equal minus rho. And this is too complicated, right? And I don't want to hijack our discussion by going into the nonlinear effects, inhomogeneity today. For homogeneous, isotropic, linear dielectrics, there are lots of qualifications here. It should be homogeneous, it should be isotropic, and also it should be linear. For that particular case, the Poisson equation, because these things turn out to be a constant, I can bring it here. So del square psi is equal to minus rho by epsilon by E. So everything that we do in electrostatics and vacuum, we simply copy it, and then instead of writing epsilon naught, we write epsilon naught times epsilon, which is the dielectric constant. Dielectric constant. It's never a constant, but the next one, please. Okay, so I've already told you this, right? So let me go in here. I have charges, electrolyte solution. Let me dissociate all the salt ions in a uniform dielectric medium. And here is one charge, another charge. There are lots of other charges, the way I was writing there. Now, what I would expect is the ions here are not going to be uniformly distributed. There are going to be correlations because one positive charge would like to see negative charges in the neighborhood. The negative charge would like to see the positive charges around its neighborhood. So what I would expect, intuitively I would expect is with respect to a reference ion, I would expect to see a cloud. And the cloud, the net charge of that cloud should be, magnitude should be the same as a reference. Oh, sorry. How do I do this? Please. Next one. Thank you. I made a mistake. Thank you. So the net charge of the cloud should be the same as this in terms of magnitude, but should have the opposite sign. And then when you go far away from the reference charge point, it's going to be homogeneous, it's going to be uniform. So let's run through the calculation, the idea. The Poisson equations are like this. Del square psi is equal to minus rho by epsilon. And I'm going to make a big assumption. Not me, Debye and Huckel did. Big assumption. The assumption is that, the density, charge density is given by Boltzmann distribution. That is not exactly correct, but that's an assumption. That means this density is given by ETC minus the Boltzmann weight, and the Boltzmann weight depends on the potential. So I have a coupling between psi on the left-hand side and psi on the right-hand side. And this is nonlinear. And this is called a Poisson-Boltzmann equation. And in order to make life easy, with very, very rare problems, we can solve this exactly. But in general, if the potential is weak, I can linearize it. If we linearize it, we get this so-called Debye-Huckel theory. Then this turns out to be del square psi is equal to kappa square psi in this regime. So linearized the Poisson-Boltzmann equation is same as the Debye-Huckel theory. And this kappa square, that kappa is same kappa that I told you before. That's related to the amount of salt that you have. The next one, please. Okay. And they already told you that kappa is reciprocal of Debye length. And you're right. And I told you kappa, Debye length is 0.7 nanometers per monovalent salt. So the range, the distance of the cloud from this ion is the Debye length. The CD is the Debye length. So that is the distance, average distance between the reference charge and the cloud, the location of the cloud. And this I have already shown you before. This is a bare electrostatic interaction. Once you screen it, it becomes a screened Coulomb interaction, Yukawa potential, if you like, and the range of that screened Coulomb interaction is the Debye length. Next one, please. Okay, now what we do is, let's move on to objects. Instead of having an infinite salty solution, suppose I have a membrane, charged membrane, planar surface with some uniform charge density, or a colloidal particle, or a polar protein with some charge density, maybe some patches, but nevertheless there's some charge density, or a cylinder with some charge density, right? Collagen bundles, for example, charge densities, or a line charge, a trivial baby-like example of a line charge. There is no dimension to it, it's infinitely long, infinitely thin line charge. How do you think about this? We do same technology, Poisson rules. Just do it. And it's doable. If you do this, you get the following intuitively obvious answers. If you take a charged membrane, the counter ions like to be close to the charges, the opposite charges. The counter ions will come and hover over that membrane. Then there will be an adsorbed layer. And there will be less adsorbed layer, diffuse, and then the bulk is homogeneous. So if I have a charge, the counter ions, let's take I have 1 molar salt in the bulk. And if you look at the profile, concentration of the counter ions, you see, look, it piles up there. Counter ions are coming close to the surface, and then it goes down and reaches the bulk value. At the same time, the co-ions, suppose I have sodium chloride and the surface is negative, so it's a positive charge. So this is a chloride ion, and let's say sodium ion, the counter co-ion means the same charge. Then there will be depletion because they don't like to be with the same charge. There is a depletion zone. Then after a certain range, it will become uniform. Intuitively obvious, but you can compute this. You can compute this exactly. This was done by Gouy-Chapman, and they calculated this exactly using Poisson-Boltzmann because of one-dimensional problem. And remarkably, the Debye length that we call was discovered by Gouy-Chapman about 20 years earlier than Debye theory. Okay, but nevertheless, we call them to be Debye length. So, how good is the Debye length? The Debye theory. So now we have an apparatus to check the validity of a Debye-Huckel theory, screen theory versus full Poisson-Boltzmann. GC, Gouy-Chapman, is a full Poisson-Boltzmann. This is a linearized Poisson-Boltzmann. And the potential as a function of distance away from the charged membrane, the difference is not that much. This is good news. This is very good news. Because that way, we could get away with the linearizing and working out the mathematics. Because you can do with the paper and pencil. You don't have to surrender ourselves to the computer. Provide why? Because the potentials are weak. If the electrical potentials are weak, roughly 3 or 4 times thermal energy, it's okay. Only when the potential becomes large, it's a problem. For example, if you look at this plot, I deliberately chose the plot to show like about 80 millivolts. Room temperature corresponds to 25 millivolts for water at room temperature, 25 millivolts. That's thermal energy. So we were talking about 3 times thermal energy. For that, the agreement is pretty good. That's already heavy potential for physiological conditions. Next one, please. Let me go to the charge sphere. You extend Debye-Huckel theory. Now I have a colloidal particle with the charge density, total charge is Q. The radius of the colloidal particle or protein is R. And then the small ion, the radius is little radius. So extra volume cannot penetrate into the protein, for example. Then I'm looking at the potential outside, right? And the electrical potential for R away from the center of mass, center of the protein has this form, which is called extended Debye-Huckel theory. And obviously, when the R is 0, we recover Yukawa, right? We recover the screened Coulomb, the original Debye. This is a generalization for finite-sized protein molecule. And on the other hand, if I look at what happens to the surface, what is the potential on the surface of this protein. There's one coming from the interior of the protein, other one coming from the cloud, and this is the negative sign. There's the opposite contribution from the cloud. This is from the interior, and that is the potential on the surface, and that is used to characterize proteins and various other objects. This is a bread and butter in colloidal science, right? These people use this quite often. Next slide, please. Okay, now let's talk about cylinders, charged cylinders. Double-stranded DNA is a very good example. This is a very beautiful classic work by two independent groups, did their work simultaneously, one from Israel, another from New York. Exact calculations, Poisson-Boltzmann, nonlinear, but you can do it because of the geometry of the problem. So they did a periodic boundary condition. Then they calculate a fraction of counter ions within a certain distance or away from the cylinder axis, right? And if you take 100 millimolar salt, this is, right, the counter ions are here, they are absorbing to the near the neighborhood of the cylinder, and then it gets accumulated and go away and away. Eventually, I get a uniform counter ions are everywhere, uniform distribution. But if I lower the ionic strength, then it's a long range. In order for the counter ions to come and bind, it gets a long range, builds up slowly. But the important thing to notice is there's no divergence in anything. It's a very continuous description. Absorbed counter ions amount is continuous as a function of distance. These are all exact calculations. Next one, please. Now let's go to the final comment I wanted to make about infinitely thin and infinitely long line charge. The reason I want to put this slide is this is a very popular concept in polyelectric physics, Manning condensation. So I wanted to tell what the underlying principle behind this idea is. I told you that for cylinders with a finite radius, there is no divergence, no problem. Now, if you do this problem, right, that is, I have an infinitely thin and infinitely long, no, minus infinity plus infinity. The charge separation is this length L. If I do this and I calculate the number of counter ions near this polymer, one line charge, it turns out to be like this: 1 over r square times gamma ZP minus 1. ZP is a charge of valency of this ion. ZP is valency of the counter ion. And gamma is the Beerem length I told you before, divided by the charge separation. And as you can see, if this number is larger than 1, this will diverge at r is equal to 0, right? If this is larger than 1, right, 1 over r positive, r goes to 0, this diverge. So what Manning argued was, I want to avoid divergence by dreaming or conjecturing that, oh, the counter ions will condense at that point. If they condense at that point, the charge separation will become longer, right? If suppose this gets condensed, now the charge separation becomes this much instead of that one. If that's the case, gamma will become lower, then I avoid divergence. So he conjectured that the degree of ionization, if this number quantity is less than 1, no problem. Degree of ionization is full. There is no condensation at all. Then after, when the quantity becomes 1, beyond that, then it will condense, the degree of ionization goes down. So this is called Manning condensation, but this is not applicable for finite side chains. So finite sized chains. Let's go to the previous one, please, if you don't mind. Because of this exact results. Okay. Next one, please. Next one. So what do we do next? That's tomorrow. So this is a picture we talked here, and then I talked over there, neutral. This is the one that we just described. We are going to put them together, and we are going to talk about the structural assembly tomorrow. Next one. If you want to know details of the derivations, right, it's kind of messy. I was just glossing over. You are most welcome to look at the literature as well as these recent book. All the derivations are given in great detail, right? Everything's worked out for the benefit of me. Thank you.
Any questions?
No questions.
No questions.
Is that right?
Okay. There is
No.
one question.
Say that again, please.
In Kuhn's model, what decides small l? I think temperature is one factor.
Small l. Okay, that's related to the persistence length, right? 2 times that a little l is the persistence length. That is the distance along which the bond orientations are correlated, and beyond which they are not going to correlate. That's dictated completely by chemistry. And in fact, the angle, right? You know, when you talk about polymer chain, right? There are every monomer is connected here, right? There's a monomer here, there's a monomer here. When you rotate it around, there are going to be dihedral angles, because sometimes this group may not be a proton, maybe it's a methyl group or a benzyl group, or whatever that group is, right? So because of that, there's going to be a lot of barriers for free rotation. All those things, if you cannot freely rotate, then it would not be flexible enough. So those things come into play to get the value of little l. So that is more like a kitchen work. We do that separately. For every chemical system, DNA, RNA, we calculate that separately. Right? Then we take that as a parameter. Once I have L as a parameter, it doesn't matter where it came from. Then for me, all polymers are the same. The personality of the polymer is associated with this value of L. That's an excellent question. It's also little.
One more question. The place where you assume charge density has a Boltzmann distribution. What is the intuition behind?
I can't hear this. Can you hear? Can you put it on? Yeah.
Hello.
Yeah. Now better. Yeah.
So the place where you assume charge density has Boltzmann distribution. What's the intuition behind that?
Yeah, just it's a Boltzmann weight, right? The probability that I'm going to have certain realization is e to the minus energy. It's not only potential, charge times potential, that's energy. E to the minus charge of a particular charge species times the potential at that point. That gives you energy, it's e to the minus E over kT. And that's the Boltzmann weight. But that's not correct, because it should be potential mean force, if you know. That's the way, rigorous way to do that, right?
I see. Thank you.
Then it becomes many body problem.
So that rho of R you are showing, that is the spatial density of the monomer. This plot, the rho of R.
This is density of the monomers, because they are all, in this particular case, it is, suppose it is not charged, then this is monomer density, number of monomers at that volume element.
Okay.
This rho is different from the rho in a Gauss law or Poisson's equation.
Mm-hmm.
That's charge density. And tomorrow we'll see rho, which is the same, because every monomer has charge. Charge density, monomer density will be the same for the bottom problem.
Hi, Muthu. Actually, I want to ask, what is the physical interpretation of that small v?
Physical interpretation of small v, this v, right?
Yeah.
There are two answers to this. Physical interpretation is basically the strength of the extra second virial coefficient. Because that's right. This is a radial distribution function, 1 minus radial distribution function, the second virial coefficient. Right? This is in the literature, in the books, they call this to be excluded volume, which is not quite right. Right? That's why people use V. Right? That's not right. This is really a combination of repulsive forces, attractive forces, resulting in an effective second virial coefficient between two segments. Right? Now, you can work out this V is also equal to, this V can be written to be 1 minus 2 chi. This chi, which we'll talk about tomorrow, is called Flory-Huggins parameter. So this chi is equal to, proportional to 1 over temperature, and the interaction between polymer and solvent minus half interaction between polymer and polymer plus interaction between solvent and solvent. So we'll take this chi, put it in here. That is your physical meaning of this. This is how the chemical mismatch between the polymer monomer and the solvent is a manifest.
Okay.
So here, this is interaction between two, van der Waals interaction between two solvent molecules, van der Waals interaction, two polymer segments, now between one polymer and solvent. This particular combination turns out to be IV.
Okay. So if Uij is only van der Waals, then at high temperature, it is repulsive because of, even if they are far apart, are they interacting?
No, they wouldn't. If R is very large, that will be 0.
Okay. Okay.
Right.
So in that case, V will be like 1. Okay. Oh,
Yeah.
Okay. Okay. I got it. Yeah.
So we have coffee now. So maybe, I'm sure there will be many questions. So we can take the discussion outside and we come back sharp at 11 o'clock for Shubha's first lecture.